percolation across, a thermodynamic metal-insulated transition, experimental traces of duality, matching lattice, and scaling.
So good afternoon. It's a great pleasure to be here. I'll be talking about some features of a metal insulated transition and and essentially how one can sort of interpret this transition in the language of percolation theory. And so this work is done primarily by Vibhu and Aniket. They're PhD students at IISER. And the samples and a lot of discussions also with Pavan and Anudeep at IISc. So basically this work is around a general theme which I've been sort of working on for the past 10 years or so, and just to look at these first order phase transitions, which are very different from the usual first order transitions in the sense that they're always hysteretic. And so it's a thermally driven transition, but regardless of how slow you go, it's hysteretic. And these are sort of governed by these spinodal singularities around these 2 points. And you see a lot of complexity. These are interesting systems because noise is really suppressed, and you see a lot of very complex, interesting features, which some of these features have been studied by some people here. But in general, I think it's an interesting system which is worth, the whole class of systems which are interesting and worth looking at. But specifically, we'll be looking at this VO2, which is one of these compounds which goes through our metal insulated transitions. There's a very sharp change in resistance over many orders of magnitude in a small temperature window. And since there's a large change in resistance, so you also see sort of a reflectivity contrast. And this is something which is very, very well studied by many people over lots of years. And so this is what you say typically see. This is some microscopic image of a small 4 cross 4 micron sample. So what we've done is that, again, just look at this transition, and you just not only study the resistance, but also study the reflectivity. And given that the 2 phases have a strong contrast in reflectivity, you would imagine that you can use the reflectivity to sort of get some kind of a precise information about the insulator phase fraction. And so you can sort of eliminate the temperature from these 2 figures and plot the normalized conductivity as a function of the, say, the metallic phase fraction, which is defined as, this the value. Yeah, so from this sort of normalization of the reflectivity, you can sort of define very roughly metallic phase fraction. And you don't need the actual values of conductivity because you're looking at linear response regime, so it's a homogeneous function. So you can just look at the ratios and can define a sort of a tilde sigma, which is like a scaled conductivity. And so what is, and then this one can do for various different sweep rates. And what you see is that you see conductivity is not a state function, and which essentially seems to imply that nucleation pathway is, even at these very slow rates, is rate dependent. And so these are, so of course you see a rate dependence, but I should sort of emphasize that these are very, very slow measurements. In the sense, these rates are very slow, so you're essentially measuring DC conductivity also. So you're just measuring DC conductivity. So the question which one would like to sort of ask, or what is sort of intriguing, is that why is there such a high symmetry in this conductivity versus the metallic phase fraction plot, and that too on the log scale. And how would you interpret the hysteresis? Of course, it's sort of tempting to think of this as a first order percolation transition or something, but yeah, these are sigma and the conductivity and the phase fraction are not conjugate variables, so one has to be careful. So of course, the symmetry point is actually the geometric mean of the resistance ratios. And so this is what you see. So what we want to do in the next 2 minutes is to just try to understand why we get this. And this is something which is very specific to 2-dimensional systems, that they have this duality symmetry. So basically, if you look at 2-dimensional systems, the curl and the divergence are the same, because if you look at a divergence of a 2-dimensional vector and put a rotation matrix, then you pick up a negative sign. So basically, curl and divergence, rotated divergence, are basically the same in 2 dimensions. And this can sort of, it's very well known that this leads to a phase interchange kind of a relationship where if you have, say, a heterogeneous medium with two kinds of substances with conductivity sigma 1 and sigma 2, and then you have the whole overall effective conductivity, then the conductivity along the one principal axis and the perpendicular orthogonal principal axis of the equivalent system or the phases interchanged is a product of the conductivities. So this is something which is, it can be shown. And if it's isotropic, then of course you don't have the axis dependence. So it's just that if you have two materials with phases interchanged, then the product is just this. And then if you have a homogeneous system, so I think homogeneity implies isotropy. So then I can think of a phase fraction, and it's just the phase fraction, 1 minus phase fraction would be this. And this would imply that at half the phase fraction, you would get the geometric mean. So this is, very simply it follows. And so this I can just write. So if I just write in terms of these dimensionless variables, then I should get the geometric mean at square root h. And then there is one more connection which one can make to percolation theory. This again, of course, a very old and celebrated result from 50 years or more, where people have done similar. So one is that when you have a square lattice of these bonds, then because it's a self-dual system, then the percolation threshold is exactly half. This is, of course, very well known. And so in some sense, you can sort of connect what you're seeing with a bond percolation problem. And so let's come back to the question. So one can immediately see that this relationship seems to be sort of satisfied, but not within a single curve. But so it's like this is the sort of the curve which you measure while heating, and this is the curve which you measure while cooling. So the two curves together seem to imply this duality relationship. There's a sort of a duality relationship between these two. And just to sort of and so if I just compare this with a like an uncorrelated Bernoulli percolation result, then you see what you see in experiments is actually quite different, and which is also to be expected because, I mean, of course, these are correlated nucleation. And so one of the questions which is not very well understood is that under such deep supersaturation, how would nucleation itself would occur? But anyway, you see that these are very different from a usual Bernoulli percolation. So let's just sort of try to see if we can sort of do this with a random resistance network. It's of course, so it's been a little difficult because we don't know the rules as to how this would go. So we just tried some brute force sort of simulations where you just take this random network, keep pushing in different bonds, and try to sort of accept a configuration when you sort of go along the curve. And if you just do that, so this is it's very rough because the system size are very small because these are very rare configurations. We don't know which ones to pick up. Anyway, so you can actually reproduce this curve maybe 40, 50 times, 100 times, after, and then you see at least qualitatively, and so these are some snapshots, and you at least qualitatively see, so this is, you can't do anything serious with this because the system sizes are too small, but you see a certain phase reversal asymmetry, like a symmetry like this. And so this is, so let me just skip this. And similarly, so of course, the two parts have different, so the insulating phase doesn't have zero resistivity, but a finite resistivity, zero conductivity. So then what you can sort of think of this as a phase transition, but with a finite magnetic field. So there's no singularity here, but then you can make a one-to-one mapping, this is again well known, between magnets and conductivity like this. And you can write down a scaling function just like you would write for magnetization versus field. You can write a scaling function for conductivity. The effective magnetic field is the conductivity ratio, where if the conductivity ratio was 0, then it's like having a critical phenomenon. And then you see that actually things do I sort of skipped a lot of details, but you can see that it's sort of and the last thing is so if you just again, if I just use this the root h as the value of the percolation threshold, then what you see is that the sort of the lattice or the path which you get while heating and the path which you get while cooling seem to obeying. So basically, the path which is taken by heating is the phased interchange dual lattice, it seems, of the paths which you get for cooling. This is true for all the curves that you measure. So this is called the matching lattice condition, and it's a very mathematical result. I don't understand, but I don't know. Maybe Arvind can probably tell me if this is not correct. But okay, so I'll stop here. So basically, just by this symmetry of the percolation certain results, you see that heating and cooling transitions of these phase transitions actually occur on phase interchange dual lattices. So that's actually something which you can experimentally see. That's the claim. All right.
Thank you, sir. Any questions?
Yes. Yes, so that question actually I thought is going to come because Deepak is not here, Sanjeev is not here, but you are here. So yeah, we tried to do that and it doesn't really make much sense. But it's something which has been an old thing for me and we've been trying that. For instance, for a very similar system, we had done this and you see some very nice scaling. So you can actually see, and the scaling again suggests this exponent suggests some mean field universality. So some other system, you can see that there's a R, like 2/3 scaling, which is a mean field exponent. So we can discuss this. But is area. So area is a little hard because again, you can do that, but again, you have to make some interpretations because these are not conjugate variables. So you have to make, so if you have a temperature, then you have to make this into entropy. So you have to, so then you have to make a lot of assumptions. You're not measuring entropy directly, you're just measuring the resistance. So you can try to do that, but then you have to, make a lot of assumptions. So the temperature shift is unambiguous, at least empirically. Yeah.
So these are classical, right? You're doing purely classical things, or are these quantum?
So the systems are what they are. These are electronic systems.
Yeah. So you are using quantum, you're doing quantum phenomena.
So this is a quantum phenomenon. The question is, how important is the quantum phenomena? So this is just a phenomenon. You're just measuring something.
Okay.
All the math, but the simulations are all classical.
So this observation that you made at the end, is that you think may be related to Onsager reciprocity or something?
That you should tell me in the sense, because how would
Because
that...
you're increasing in one way and then coming back the other way.
But reciprocity, as I would understand, is just that you have a given fixed configuration. Yeah. I don't know if it's used in some other context also, but you have a fixed configuration and you're just looking at... so it's one is this relationship between the components of the tensor. So could you sort of tell me what exactly you sort of mean by sort of
what I was thinking of was how you went from one equilibrium to one non-equilibrium to another versus going back.
So these are all equilibrium configurations.
Okay.
So you just create these disordered configurations through the phase fraction. And so you have a whole set of, so you have a set of lattices and you're going one way, and then there's a dual lattice which is phase reverse dual lattice. So these are all equilibrium configurations, whole set of them. And the whole process of this phase transformation is taking you one way this way, other ways is phase reverse dual. So that's the thing.
If not, let's thank speaker.